to our 6.04 Polygon Similarity lesson. Here's an application that we can look at that involves something that applies in the real world, which is the possibility that Leonardo da Vinci, who in the early 1500s painted the Mona Lisa, may have used a preliminary sketch that was a scaled down version of the actual painting itself. And so scaled down means it's smaller, and we're missing the width of that preliminary sketch, and we're going to use the original sketch to find that missing width. To do that, we're going to use the similarity property that exists between the two figures. If they are in fact similar, then we can set up a proportion, and a proportion is where we take the corresponding sides and we write ratios of those sides. For example, I know that this side length here is going to correspond with this width. I can call this side length x because I don't know its value, but I'm going to find its value. I can divide that by the corresponding side length on the actual painting. Likewise, I know that 8 corresponds with 30 in terms of the height of the portrait and the painting. And so that would be equal to 8 over 30. Everything's measured in inches, by the way, so it's always important to check what unit of measurement you're using, because you want to make sure that they usually are in the same metric or the same form of measurement, and they are. So how do we use the cross product property? Well, what we do is we multiply across our equal sign here. We multiply from the denominator to that numerator and from the numerator to that denominator. So this proportion becomes an equation that doesn't have any fractions at all. It becomes 30 times x equal to 8 times 21. Or you can just write it using the dot that we talked about for multiplication. So that's going to equal 30x, and of course this is going to equal 168. And then we just have an equation here where we're going to have to solve for x. So we'll divide both sides by 30, and we end up getting 5.6 inches. Or you can use the symbol for inches. So we actually now know the width of that potential preliminary sketch that Leonardo used prior to having painted the Mona Lisa. And this is an example of the technique that you're going to need in order to solve 2 of the 3 exit ticket problems that you have. So I want you to have a moment to try the cross product property yourself really quick, and let's see what we come up with. So when you have x over 6 equal to 3 over 10, when you cross multiply, we get 10x is equal to 18. Now notice how I just went ahead and multiplied 6 and 3 right away, and then I wrote that product down here. That's 18. And then 10 times x is just 10x. So I can do that, of course. And then after dividing by 10 on both sides, I end up getting 1.8 for my answer. So we should end up with 1.8 as the answer here for the value of x. Now remember from the other day we talked about what similarity actually means and how we're comparing objects that are either larger or smaller to the original object, and we refer to that as a dilation actually from the previous units that we've discussed with transformations. So really when we're looking at similar figures, we're looking at some form of a dilation that's happened, whether it be larger or smaller in the circumstances that we're given. And during that transformation, the side lengths are either getting longer or they're getting smaller. They're changing. Now what doesn't change is the angles. The corresponding angles are going to be congruent to each other no matter what. So remember we had that A corresponded with X, we have that B corresponds with Y, and we have that C corresponds with Z. So if we have triangle ABC as an example, triangle XYZ as an example, notice how again A matches up with X, we have that B matches with Y, and we have that C matches with Z. And that can very easily reveal the corresponding angles of 2 similar figures like we have right here. We also have the corresponding sides, which of course are proportional to each other. And proportional means that the corresponding sides have equal ratios. So for example, we have that AB matches up with XY. We have that BC matches up with YZ. We have that AC matches up with XZ. And you're looking over to the right and you realize, okay, so I have the, AB matches up with XY, so I'm writing a ratio of those 2 lengths right here, right, that you can see right there. I'll just put it in a pen. So AB over XY So it's, we have triangle, again, ABC is similar to triangle XYZ. If you look at the similarity statement that I just wrote, you can see that the first two letters match up. So if I write a ratio of those two, I get the scale factor. If you compare, for example, the last two letters, BC matches with YZ, which it does. That's actually at the very bottom there that you see right here. And then, of course, lastly, we know that you have the first and last letter that I haven't referenced yet, right? So you have AC corresponding to XZ, and you can see that that's represented right here. And again, they're all the same because this number that you see right here is what we refer to as, among many things, the scale factor. Okay, so this is the scale factor of our figure. So in light of that fact, we can see that with a similar set of triangles that we have, we can label our vertices A, B, C, and T, C, D. And we can see from the diagram which angles correspond. We know that A and T correspond, we know that B and C correspond, and we know that E and D correspond. And in this case, I need to make sure to label that side length properly. It does say E, not C, so I'm going to change that to E there, and that fixes that right away. And so we have E matches up with D. So the real question now is, okay, if we have that, we know angle A is 61 degrees and C is 55 degrees. But remember that this is a similar pair of triangles. So we know that we have corresponding congruent angles. So congruent corresponding angles. That means they're all the same. So angle B is also 55 degrees. Angle T is also 61 degrees. So really we're just missing the third angle in a triangle. And we know exactly how to deal with that because we can use the triangle sum theorem. The triangle sum theorem will allow us to take 180 degrees and subtract the measure of the other two angles combined together. So 61 plus 55. That's 180 degrees minus 116 degrees, and that is going to equal 64 degrees. That is going to equal the measure of angle D. Okay, so we're using our triangle sum theorem here in combination with our knowledge that the corresponding angles are always congruent in similar figures like these two triangles. So looking at that respect, we need to be able to work with similarity statements and identify them. And one of the things that I like to do is also think about size as well. Look, for example, over here at EF. EF is the smallest side length of the figure. And also, E to D is the second smallest, right? So the two side lengths that match with that would be KG and would be KH. So I can see here that when I write out my similarity statement, I already know that if I go from E to F as an example, then the first two letters of my other statement will have to be KG. That just leaves me with my third letter, which of course is D, and in this case it would be H. That's a similarity statement. It also shows you as well, if I circle them, that angle E corresponds with angle K. So I know that angle E is congruent to angle K. I know that angle F is congruent to angle G, and angle D is congruent to angle H. And again, you can see that F corresponds with G and D corresponds with H. So they're congruent to each other. And if you look, you can actually see that the order that I wrote earlier here matches with that particular column order of letters or vertices that I have, just as it does over here and over here. So if I want to come up with an equivalent similarity statement, I could also just flip this around and say DFE is similar to triangle HGK. And so those are going to end up being correct similarity statements based off of my diagram there on the left. Here you can do it again. In this case, what we're going to do first is write the ratios. And we kind of already started doing that as well. So if I kind of use those sets that I had before, I identified segments first and I wrote a similarity statement. So now that I've seen that, I can say, okay, this is going to end up being, EF divided by KG. And the next one will be ED divided by KH. And then the last one is going to be DF divided by HG. So the numbers, if I plug them in, are 3 and 6, 4 and 8, and then we have 6, and 12. And each and every one of those reduces to the same number, which is going to be 1/2, right? So do each of these reduce to equal the same proportion? The answer is yes, they do. What is the importance of that? Well, that just proves that the two figures are similar. So remember how we talked about if you want to show that two pairs of figures or two polygons are similar, if you can show that the corresponding sides have equal ratios like they do here, then you've just confirmed that they're similar to each other. In light of that fact, we can go ahead and actually utilize that technique to help figure out missing lengths. So for example, we're actually missing A prime B prime, and we're missing C prime B prime. So how do we find those lengths in our image, right? This is the image, knowing that this is our pre-image and we have all of those lengths available. Well, it's nice to know that one of the lengths in the image is actually known, because I can make a comparison with that and that length right there. So let's go ahead and think about that. We have A prime C prime over AC. We will have B prime C prime over BC, and we'll have A prime B prime over AB. We know A prime C prime is 8. We know that AC is 12. We actually do not have B prime C prime, but we do know that its corresponding side is 9, and we do not have A prime B prime, but we know its corresponding side is 18. So looking at A prime B prime, keep in mind that this fraction right here actually simplifies to 2 over 3. How do I know that? Well, 8 over 12 reduces. You can divide top and bottom by 4, so it reduces down to 2/3. If you can reduce the fraction, I sometimes recommend that because it is a little bit easier to deal with when you do. So A prime B prime, if I divide that by 18, that should equal 2 over 3. Then I can just cross multiply. So I get 3 times A prime B prime equal to 2 times 18, which is 36. Then I can divide both sides by 3, and I end up with 12. So I know that A prime B prime is going to be 12. Likewise, with B prime C prime, I'm dividing it by 9, and that should also equal 2 over 3. So I can go ahead and cross multiply here. So I get 3 times B prime C prime equal to 2 times 9, which is 18. And then I can divide both sides by 3 in order to get 6. So now I have both of the missing lengths of that image that we were originally given, and I'm utilizing the proportions and the cross product property or the cross multiplication technique to solve those particular missing lengths right there. So could I have used 8/12 instead of 2/3? Yes, I could have used those instead. If you want to use the original ratio given to you or that you write up yourself, then you're able to do that. That's perfectly acceptable. In the final problem here, we have a person standing over there on the left that's 1.5 meters tall, and he's about 2.75 meters away from a point on the ground. That exact same point also lies 33 meters away from the base of the tree. Our task is to recognize that these triangles that are created are similar to each other, and we also can see that we can come up with a proportion to help figure out the missing length of the tree, the height of the tree specifically. So we recognize that the height of the person and the height of the tree correspond with each other. So we can write h divided by 1.5 will equal this length right here corresponds with this length right here. So that's 33 divided by 2.75. So that's the proportion. That's the first step. So now I can cross multiply. So I have 2.75 times h. This is going to equal our value there, which I've written, and then we have 1.5 times 33, and 1.5 times 33 is 49.5. Then I can go ahead and divide both sides by 2.75, and I get the value or the height of the tree, and that height is going to end up being 18 meters tall. So we have an 18-meter tall tree, and all I had to do was cross multiply, which is exactly what we're doing here, after setting up my proportion, and then I can solve for my variable. So your exit ticket requires that you pay attention to your order of letters as well as the lengths that are provided. You're going to want to set up a proportion, and you're going to want to cross multiply in order to solve the first two questions of your exit ticket. So again, labeling is also very, very helpful. I certainly would encourage you to do that. And then your last question over there, you're going to find the missing angle D. We just covered a problem just like that in this presentation today. That is going to represent your lesson for 6.04, Prove Polygon Similarity.